Let's look at this expression 1 plus 1 over n raised to the n. We're going to plug in some numbers. First of all, let's take a look at n equals 0. So for n equals 0, you can see that we're going to be dividing by 0, so we can't do that. We're also going to skip over negative numbers. If you want to try playing around with some negative numbers, you're welcome to do that. I'm just going to stick with positive numbers here. So if we plug in 1, so if n equals 1, then we get 1 plus 1 over 1 raised to the 1, which is 2 to the 1, which is 2. If we plug in n equals 2, then we get 1 plus 1 over 2 raised to the 2, which equals 1.5 raised to the 2, which is 2.25. Okay, so these numbers are growing. They're getting a little bit bigger each time. If we look at n equals 3, actually scratch that. Let's skip up to n equals 10. So then that's 1 plus 1 over 10 to the 10, which is 1.1 to the 10, which is approximately 2.6. We'll round it off to 2.6. So again, getting bigger. Let's jump way up. Let's do n equals 100. Okay, so that's 1 plus 1 over n. 1 over 100 raised to the 100, which is 1.01 raised to the 100. If you calculate that, you get approximately 2.7705. Let's go even higher. Let's go up to n equals 1,000. Okay, then we get 1 plus 1 over 1,000 to the 1,000, and you get from that approximately 2.717. If you do the same thing, and I'll stop doing calculations here now, but if you do the same thing with n equals 10,000, you get approximately 2.718. And this is the number we're getting to. So this is a new number that we're talking about. We call it e. And it's derived, well, one of the ways it's derived is from this expression here. And as you plug in bigger and bigger and bigger numbers, you get closer and closer and closer to e. The actual value of e is not something I can tell you. It's kind of like pi. It's irrational. It goes on forever. There's no pattern to it. So in that way, it's much the same as pi. But the first few digits are written down here, 2.71828. And so we say as n tends towards infinity, as we plug in bigger and bigger numbers for n, we get closer and closer to this number e. E is called the natural base. We'll get more into that later. It's because it's a very nice number for doing exponents. So if we use e as the base of our power, there's some nice things that happen. We'll get more into that later. For now, we're just going to do a little bit of work with it. Okay, at the bottom here, let's simplify some of these expressions. So we're just going to be using our exponent rules here. So e to the second times e to the fifth, add those exponents, and we get e to the seventh. With a fraction over division, the exponents get subtracted. So we have the 12 divided by 3 is 4. E to the fifth divided by e to the third is e to the second. And then the last one over here, we've got a negative exponent. Let's take care of that first. So the 5 stays on top because that negative exponent is only on e, it's not on 5. So that'll stay right where it is. And then we have that whole thing raised to the second power. So that's going to be 5 squared, which is 25, over e to the 3x to the second. Multiply those exponents and we get e to the 6x. Now let's use a calculator to figure this out. So most calculators have this e. If you have a scientific calculator or a graphing calculator, it definitely will. If you have the TI 30X, it's going to be two buttons down from the second button. It's right above the one that says LN. It's that same button. If you have a TI 83 or 84, one of those graphing calculators, it's 2 up from the on button. So you just hit that, and then you can type in whatever exponent, the e to the x thing. Type in whatever exponent. In this case, 4. So if you do e to the 4, you get approximately 54.6. And again, we're going to have to round this off because e is irrational. There is no end to it, so we're going to have to round it off. E to the negative 0.09. Again, plug in, hit second, e to the x, then type in negative 0.09, and you should get approximately 0.9. Now let's start graphing a function with e. So since this is irrational, it's not going to be possible for us to get some nice numbers. So everything we plug in here, we're going to get some nasty decimal that we're going to have to round off. And again, that's just because e is irrational. So there's no way we could possibly get nice numbers unless the exponent is 0, because anything to the 0 is 1. That's the only nice number that we're going to get here. Okay, so let's just make a table and start plugging in some stuff. And we're going to want to use our calculators here again, using the e to the x function on there, or the operation there. So we plug in 3, you should get about 0.05, and I'm rounding the numbers off again. If we plug in negative 2, you should get about 0.1. Plug in negative 1, you should get about 0.4. At 0, again, anything to the 0 is 1. And then I'll continue the table to the right here. If you plug in, let's see, I left off at 1. Okay, so that gives you about 2.7, so that's e to the first, which is just e. E is about 2.7. And then to the second power is 7.4, approximately. And then to the third power we get, again, since these exponential functions grow so quickly, we get this real big number 20.1, which we're obviously not going to be able to get on this graph, but you can see that it's going to go way off the graph there if we go past 2. Okay, so let's start plotting these points. At negative 3, we have 0.05, real close to the x-axis there. At negative 2, we have 0.1, again, real close to the x-axis. 0.4 at negative 1, so just under half. Then at 0, we have 1. At 1, we have 2.7. At 2, we have 7.4. And then I'm not going to graph that last one. But you can see this gives us that exponential shape with the asymptote here at the x-axis. And then it goes up and just explodes there around 1, 2, 3. It just explodes, gets really, really big, really, really fast. All right, so that is what the function e to the x looks like. Again, it looks just like any other exponential function that we've looked at. It's just that we have a bunch of nasty numbers here since e is irrational. If we look at the domain and range, same as any other exponential function. The domain is all real numbers, which I'm going to use this symbol for, because we can plug in anything. We can raise anything to any power. There's no limit on what we can raise, what powers we can raise things to. For the range, well, we only have positive values here. So we have this asymptote that gets infinitely close to 0, but it never actually touches 0, never actually reaches 0, and it doesn't cross 0, so we don't get any negative numbers here. So it's going to be just y is greater than 0 and strictly greater than, again, not greater than or equal to. Okay, let's graph one more of these functions with e. So this one has e to the x minus 2, so that's going to shift the graph 2 to the right. And then it has the plus 1, which will shift the graph up 1. Again, pull out that calculator for these calculations. If you plug in, we'll start with negative 3. And I'm going to pause the video here and fill in the table just to save time. Okay, there's all the rest of the table. You're welcome to check those if you want. But that's what you get if you plug in those numbers. So you can see on the left side with the negative 3, negative 2, negative 1, 0, those are all real close to 1. So our asymptote has moved up 1, and that's because of this plus 1 right here. That moves the entire graph up 1, so our asymptote shifts up 1 as well. So let's start plotting these points. Negative 3 just above 1, again just above 1, just above 1 for all of those. And then at 1, x equals 1, that's where we start getting a little bit farther away from a y value of 1. And we have a y value of 2, 3.7, and then 8.4, and it'll just keep getting bigger and bigger and bigger. And so we have this asymptote at 1, and then it just explodes here and goes way, way up. So you can see that this graph does look like it's shifted up 1 from the red one, and it's shifted 2 units to the right from the red one. So that's how those shifts work. As far as the domain and range goes, again, domain is the same as all of these exponential functions. It's all real numbers. And the range here is anything greater than the asymptote. So y is greater than 1. You may have noticed as you looked at this way of getting e, this thing right here circled in blue, that looks very, very similar to the compound interest formula that we used in one of the previous lessons. So we can combine these together and do a little bit of calculus, and we come up with this piece here kind of cancels down or simplifies down to e, and so we end up with this formula here for continuously compounding interest. So you can see as n, as this rate here, as the number of times compounding gets bigger and bigger and bigger, as we go to infinite compounding, that would be continuously compounding every instant it's compounding again, we get e. This kind of arises from this. So we get this formula p times e to the rt. This is often referred to as PERT, P-E-R-T. This is how we get continuously compounding interest. So A is the account balance, P is the principal. Again, principal is the amount that you put in initially. R is the rate, again expressed as a decimal, and T is the amount of time, typically in years. So let's plug some things into this formula and do a little calculation here. So the new account balance after this interest accrues is going to be the principal, which is 4,000, times E, raised to the interest rate, which again we use as a decimal, so the percentage, to switch from percent to decimal, just divide by 100, and then times the number of years, which in this case is 1. So then you'll want to grab your calculator, hit second e to the x, and get that 0.06 times 1 in the e to the x, and then multiply by 4,000, and you should get approximately 4,247.35 approximately. Again, since e is irrational, we will always get an irrational answer here, so we're going to have to just round it off to the nearest cent.